So as with many questions, a really good way to start is to start by drawing a diagram. So we've got this disk, something like this, and it's got a radius r, and we're trying to find the voltage at a point which is a distance h above the center of the disk. And across the disk, it's got some charge, capital Q, which is evenly distributed. Now, in order to do this, we're going to want to exploit symmetry as much as possible, like we usually do. And so what we'll do is we'll consider a little ring of charge here. So let's take this little ring here. And we'll let this ring have a radius r, and it's got a width which is given by dr. So this was kind of hinted at in the question because it told us what the voltage of a ring was. So the voltage of a ring is equal to kq over the square root of r squared plus h squared, where q is the charge on the ring. So if we can work out how much charge is on this ring here, we'll know how much this ring contributes to the point up here. And then what we can do is we can sum together all the rings, so integrate over the entire disk to get the total voltage. So let's call dq the charge on this ring. Let dq equal charge on ring. And if we knew the surface charge density, it would be equal to that surface charge density times the surface area of the ring. So let's see if we can calculate these two things. So surface charge density is equal to the total charge divided by the area. And we know the surface area of this disk, it's got a radius capital R, so the area is given by pi r squared. So that's sigma, and dA, there's the surface area of this ring here. So if we imagined cutting this and spreading it out, so it's spread out like some length here, then it's got a width dr, and it's got a length given by 2 pi r. So that's from there to there. And so the total area dA is given by 2 pi r dr. Okay, so we can substitute these in here, and we've got q over pi r squared times 2 pi r dr. These pi's cancel, and we end up with this is equal to 2q r dr over r squared. Okay, so we can say that the amount that one ring contributes, we'll call it dv, because it's a very incremental ring with only width dr, is given by k times q, which is our dq here. So this is times 2q r dr over r squared, and then we've got this times r squared plus h squared. So if we want to get the total voltage, we're going to have to integrate this expression over all the radii. So if we integrated this and we integrated this, then we'd end up with this thing here is equal to the voltage, and this thing here, we'll want to integrate it from radius 0 up to radius r, because capital R is the outside of our disk. So let's pull the constants out the front, apart from the 2, we'll leave the 2 there. So we've got this is equal to k times q divided by r squared. Capital R isn't a variable, it's the radius of the disk, it's little r which is varying. So then we're integrating from 0 to r, and we've got 2r dr over the square root of r squared plus h squared, which you can possibly see how to do really quickly, but how I'm going to do it is with a substitution. So I'll let u equal r squared plus h squared. So this tells me that du dr is equal to 2r. So I can see that du is equal to 2r dr, which was why I left my 2 inside this integral here. So I can replace my integral now. I've still got the voltage, and I've got the kq on r squared out the front. And now up the top here, I've got du, and down the bottom, this is equal to the square root of u. And looking at my limits, when r is 0, I've got h squared, and when little r is big R, I've got r squared plus h squared. So I can write this as kq on r squared times the integral from h squared to r squared plus h squared of u to the minus a half du, which is then not too hard to integrate. Hopefully you can see that that is going to be equal to, well, I've got my constant out the front, and then I'll end up with 2u to the 1/2 from h squared to r squared plus h squared. And so, sorry, my k's are starting to look a bit like my r's. That's an r there. And so this is equal to kq over r squared times 2 times, we've got the square root of r squared plus h squared minus the square root of h squared. Square root of h squared is just h, so I can write this as 2kq on r squared times the square root of r squared plus h squared minus h.